and after that we will get into capacitors. So we talk about we spoke about conductors in detail. Today we'll talk about dielectrics. You remember in chapter 1, dielectrics are like insulating material which are not conductors, dielectrics, and we will also talk about what happens when you polarize them. Dielectrics and polarization, this is your topic. Okay, so we get into first understanding what are dielectrics. Dielectrics. So dielectrics are substances which do not conduct electricity at all. So we can write they are non-conducting material, and all magic will be done by them only. Non-conducting material. Examples can be glass, mica, rubber, paper, etc. These are known as dielectrics. Dielectrics have no free electrons. Keep them as points. Okay, dielectrics have no free electrons, and charges cannot move freely. Obviously, that's why they don't conduct. Charges cannot move freely. And the next one is, if you remember, the internal electric field inside a conductor was 0. Here we will say internal field is not 0 but is reduced. Internal field is not 0 but is reduced. This is what we will be trying to understand. Internal field. Okay. So now let's see in an external field. In an external field, say the external field is E naught. You have applied external field E naught. Let's see what is the behavior of dielectrics and conductors. Conductors you have already studied yesterday, but we'll just recollect. Okay. If you are a conductor, and then if you read these notes, they are more than enough for you. Free electrons move and redistribute. Remember that free electrons move and redistribute. If there are any induced charges, they are always on the surface. Induced charges appear on surface. Recall, if you are a charged conductor, then your induced charges. So the E internal, okay, plus the E external will always be equal to 0. So we say E net is always equal to 0. This is what we studied yesterday for a conductor. Now let's see what happens for a dielectric. You have already written that in a dielectric, the electric field is not 0, but it is reduced. So here we will say charges cannot move freely. Move freely. That is point number 1. Point number 2, there is a slight shift. Okay, this is the difference. Okay, here there is redistribution and free movement. Here there will be just a slight shift. Plus and minus charges, there are charges inside and they will just move. Slight shift in charges in positive and negative charges. So due to this slight shift, you will do what? Try understand. In a dielectric, you will have a slight shift of positive and negative charge, small. So actually a dipole will be formed. Small or tiny dipoles are formed. Induced charges. This is the summary. We are going to study it in detail. Induced charges oppose E naught One minute, just hello. अच्छा, थैंक यू, उसी के लिए मिस कॉल तो दिया था। ओके, चलिए, थैंक यू। ठीक है, ठीक है, ओके ओके, थैंक यू, थैंक यू। Okay, so here we say induced charges oppose E naught but cannot cancel it. Might be appearing Greek and Latin to you, so don't worry, we will see why this happens. So your E net will be equal to whatever E0 you had minus E induced. Okay, means I'm putting here plus to show that the sign between them is one is a minus sign. Okay, where you write absolute value of En is always less than the absolute value of E naught, and E net is not equal to 0. Children, just understand this. This is a dipole, a dielectric is a substance like this, okay? Inside the dielectrics, the positive and negative will just have slight separations. So these will be individually like a dipole. Why they form a dipole, that we will see now. Due to these dipoles, if you consider it like a surface like this, on the surface there will be plus signs coming up. This is one dipole, then this is again one dipole, then this is again one dipole, again one dipole, and again on this surface minus. So this is called the surface charges. These surface charges are going to induce an electric field, but that will be very small. So therefore, this electric field, these induced charges cannot cancel the external electric field. So there will be a E net in the case of a dielectric. But this is a summary. Please understand. In a conductor, if you apply an external electric field, nothing happens inside the conductor. But here, E net is 0. Here, E net is not 0. Okay? So now we try to understand what is polarization, why this is happening. Okay. So for that, first let us understand polar and non-polar molecules. This is chemistry. Let us first see whether you any idea of polar and non-polar. Yeah, no, not shift in concentration exactly. So let's say you take water. Water has got hydrogen and oxygen. What is water? H2O. So you have hydrogen, you have oxygen, and you have another hydrogen. Okay. So oxygen has got how many electrons on the outermost orbital? 6 electrons on the outermost orbital. So this is 1, 2, this is 3, 4, 5, and 6. This is pairing with hydrogen. Clear? Now these are called bond pairs. There are and other pairs are known as lone pairs. These lone pairs will produce something which is known as electronegativity. They will try to shift, they'll try to pull this shared electrons towards itself. This is known as electronegativity. And oxygen's electronegativity, you should always remember this formula, FON. Fluorine is highest, followed by oxygen, followed by nitrogen. Highest electron negativity. Electron negativity means whenever there is a shared pair of electron, one of the atom will be actually pulling it more towards itself. So oxygen pulls the shared pair. Once it pulls the shared pair, means it has pulled this. So oxygen develops a delta negative charge and hydrogen develops a delta positive charge. This is called a polar molecule. Whereas if you see carbon dioxide does not have any lone pair of electrons. So these will never be linear. If you will study that water has got 109 degree 28 minutes sort of a structure because it will be pulled along. These are called polar. Is it clear? A polar molecule is that which is formed from a covalent bond, but there will be a partial charge which will be formed on either of the ions. This is because of the electron negativity of one of the atoms. As such, hydrogen water forms hydrogen bonding. This hydrogen will bond with another molecule's oxygen. This is polar. And non-polars are what? Non-polars, you will see them linear. Have you understood? Same concept we will use here. So let us first see what happens between polar and non-polar molecules. So let's take non-polar. So try to understand the story. You are studying dielectrics, and inside dielectrics, you are studying non-polar dielectrics now. Non-polar molecules. Non-polars are like hydrogen, oxygen molecule, carbon dioxide. These are all non-polar. In the case of non-polar, positive and negative centers coincide. Positive and negative centers coincide, and no permanent dipole moment is seen. You will not have any permanent dipole moment. Look, whatever were the positive centers and the negative centers, they'll just coincide with each other, and no permanent dipole moment will be seen. This is in the case of non-polar molecules. Whereas if you see polar molecules, who are our polar molecules? Water, HCl, these are all polar molecules. Positive and negative centers are separated, and permanent dipole moment exists. Permanent dipole moment exists. So our story starts. What is the dielectric? Someone who does not conduct electricity, someone who does not have free electrons, someone whose free electrons or the positive and negative charges under the influence of an external electric field just shift a little and cause a net dipole moment. But you see, in the first section you wrote that small tiny dipoles are formed, and now you are writing that no permanent dipole is seen. This is when they are neutral. And this condition you had written when an external electric field is applied. That is what we are going to study. If the substance, for example, this mouse trackpad, if I consider this as a piece of a dielectric, then in this dielectric, if it is polar, then there is no permanent, if this is non-polar, there is no permanent dipole moment. If this is polar, there is the dipole moment because the centers do not coincide. Here the centers coincide. Is this much understood? Now we will see, we will apply a electric field. Now, in an external electric field. Acha, last time when I wrote this statement, children, you were comparing between conductors and dielectric. This time we are going to compare between polar and non-polar. So let's see non-polar molecules. Okay. Before you write for non-polar, just think what used to happen in non-polars. Non-polar molecules are those in which there is no net dipole moment as positive and negative centers coincide. Now you have given an electric field. What do you expect? As soon as you, although they have, see, on this hand of mine, there's a positive charge, there's a negative charge. Now I have given, so there's no net dipole moment. Now I have given an electric field. What do you expect? The positive will move towards the electric field. The negative will move towards away from the electric field. Don't you think a dipole moment will be created? Yes. So that's what we are going to write now. So we write, without electric field, there is no dipole moment. This is what you just wrote, right? Now, once you apply electric field with an electric field, positive and negative charges shift slightly in opposite direction. Each molecule develops an induced dipole moment. So what did you do? You have a dielectric. A dielectric may be polar or non-polar. If the dielectric is non-polar, there is no sort of dipole moment in it. You applied an external electric field. You created a separation between the positive and negative centers. So you induced a net dipole moment, induced dipole moment, and this is what is known as polarization. This is called polarization. You know the meaning of the word polarization. Due to the impact of any external agency, if you can make somebody dance to your tunes, usually this word is used in vote bank politics. If you can make someone dance to your tunes, you say that you have polarized that vote bank. And similarly, you have polarized it out here. Okay. Why did you polarize it? Now because you have created a dipole moment. Let's see what happens in polar molecules. Remember children, polar molecules, even if you don't apply any electric field, there was a net dipole moment already with them. Okay. So here we say dipole moment exists, but exists randomly. This is without electric field. Dipole moment exists randomly. Means your particular dielectric will be seen like this. Plus minus, plus minus, plus minus. There are dipole moments, but they are in random direction. So total dipole moment average was taken as 0. Although there is a dipole moment in them, total was taken as 0. With E, a net dipole moment develops. Stories just like conductors. In conductors, imagine these were like free electrons moving randomly. You gave the electric field, they got aligned in one direction. Now you gave an electric field, they will get aligned in one direction. And what is that one direction? It is something like this. This is the dielectric. This is just the surface of the dielectric. So on surfaces, you will get some charges that will be developed. Opposite. Now this is one dipole moment. Did you understand? Sorry, this is one dipole. Just see children, this is one dipole. Beside it will come another dipole. Beside it will come another dipole. So do you understand now? The dielectrics two surfaces will carry now charges. One side will carry positive, positive, positive. One side will carry negative, negative. So a surface charge density will be induced. So you can just make this. Okay. So similarly, you will get minus, 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 minus out here. So this also is known as polarized. So what is the inference you develop? If you apply an external electric field to a dielectric, you can always polarize it, whether the dielectric is polar or it is non-polar. Non-polars did not have any dipole moment. Polars had a dipole moment which was random. I applied an electric field. I can create an induced dipole moment here also. I can create an induced dipole moment here also. That's why you wrote in your first column. Also, if you see on the left hand side of your page, you wrote in an electric field, you wrote conductors will have surface charges which will go on the right. Net electric field is 0. Here you will have induced charges, and an induced dipole moment will give an induced field. It will just reduce the overall electric field, but there will be a net field. So we now say in a position to say what is polarization. So polarization mathematically is dipole moment per unit volume. So it's dipole moment per unit volume. That is net dipole moment divided by volume. This is polarization. Just think it like civics. How many people you could polarize divided by the population you are trying to polarize. Net dipole moment per unit volume. Now there is one expression, it's that CBSE or NCERT doesn't talk about it, they've just written an expression. We will also write it. It says for linear isotropic, we will understand what the meaning says. Isotropic dielectrics. Isotropic. Tropic word comes from tropical. Iso means same. Isotropical, similar tropical. So here isotropic means similar physical and mechanical properties. Take two dielectrics which have similar physical and mechanical properties, means the strength is almost same, and linear, not that curved word, linear, single pattern. Okay, here they say polarization is given by the formula epsilon naught, and then there is a quantity called xi e into E. We will understand epsilon naught, you know, permittivity of free space, where epsilon naught is known as, you will not get any maths out from here, but you may get concept based question. What happens if this increases? Permittivity of free space. Free space. E is the electric field that you are applying. E is the electric field. Now try and understand. Try and understand. I'll give you one analogy and you'll understand it. You're trying to polarize a mass for a voting bank. What does it depend upon? How much effective is your speech? That is electric field. Permittivity of free space. How much my speech can reach them? Permittivity. Social media, print media, more. And what is this, you think? What should it be? Whom are you trying to polarize? The people. Are they willing to polarize? This is called electrical susceptibility. How much you are submissive in front of an electrical field, which in other words we call willingness to polarize, can be understood as willingness to polarize. So xi e is known as electrical susceptibility. In other words, this means willingness to polarize. I can polarize you if my statements or my lectures are very, very strong. The media allows my lecture to enter your ears, and you yourself are also submissive in front of me, or willingness to, you show willingness to polarize. Only then I can polarize. That's the definition. Now, since you have polarized, I go by this drawing. Since you have polarized, you have created some surface charges. So let's talk about these surface charges now. Surface charges on a polarized dielectric. Is the concept getting clear? This dielectric will have a net electric field inside it. It is not like a conductor where the electric field will be zero, because in a conductor, if the free charges have the ability to redistribute and nullify it, here they cannot nullify. They can just move a little. In moving a little, they will either create a dipole or they will coincide with their centers. If they coincide with centers, apply electric field, they shift. And if they had a dipole, they were all non-aligned, they got aligned. In either cases, there is a net dipole moment, and you will see some surface charges. Okay? So we write, when dipoles align, now since you're polarized, so the dipoles align. So when dipoles align, let's see what all we are thinking. Inside the dielectric, positive end of one dipole is cancelled by negative end of another dipole. Children, what did I mean by this? Look, inside the dipole, positive end of one end is nullified by negative on another. Have you understood? So inside all the charges will get nullified, but externally it will show one side one surface, one side just the opposite surface. That is what we are going to write. Okay, so we write, so that's what I've written. Surface charges on a polarized dielectric, when the dipoles align, when this align inside the dipole, what is happening? This is happening. And at surface, cancellation is incomplete. So on left hand side, I may have a polarized positive charge density, and on right hand side, I may have a polarized negative charge density. And these are known as my bound charges. Here, net volume charge. See, inside is a volume. So here we will write rho is equal to 0. There is no net volume charge. Did you understand? There were many plus and minus. Why is sir still writing them as 0? I am writing them as 0 because each plus is being cancelled by a minus inside. And so the net volume charge is 0. Please try to understand. Whereas on the surface, cancellation is incomplete, as a result of which you have a surface charge distribution positive on the left. It is not necessarily only on left, it can be on right, but whatever side is positive, the other side will be negative. Typically in your diagram, this is polarized positive charge density, polarized negative charge density. And this will be helpful in our capacitor. ठीक है, इतना तक समझ में आया? Very good. चलो next. So our final summary we say effect of polarization on electric field. Effect of polarization on electric field. What is this? There was a dielectric who was happily standing alone. What did you do? You brought an electric field on that dipole near that dielectric. So the dielectric got a net dipole moment associated with it. Due to the net dipole moment and the aligned nature of it, surface charge was created. Volume charge is 0. Now, are these surface charge going to hamper that electric field? Means what we are trying to say is that there is an external electric field now. This was the external electric field E0 which you had applied. Now, due to this and this, is there any impact on the E0, the one that you had brought, the one that had actually polarized your dipole? So we'll see induced charges, but these induced charges are very less as compared to a conductor. Create their own electric field. So you get what is known as an induced field. Induced field will now opposes external field. But whereas in the case of conductors, they cancel, here you won't cancel. This is exactly the first part that you wrote. So this is your external electric field. This is your induced electric field. So my E becomes equal to E0 minus EP. Okay, EP means electric field due to polarization. This is E0. E0 minus EP. So net field inside dielectric is reduced. In short, just write these two statements. If you were a conductor, you had more charges. More charges means more free charges. So E becomes 0. And if you are a dielectric, your, should I write more? I'll write, it's better to write this way. Charges move. Here charges shift. Now you see your first statement, the very first comparison that you had done, E becomes smaller. That's all. That's all about polarization and dielectrics. You write down, we'll have a quick chat on this before we move to capacitors and capacitance. So if you have a conductor has got lot many free electrons in it. As a result, the electrons are free to move, they redistribute, the net electric field becomes 0. But if you compare it with a dielectric, the charges are not free to move, they just shift. In a dielectric, when a net electric field is applied or an external electric field is applied, dipoles are created, the dipoles align themselves. Due to this alignment, the dipoles will create a layer of positive charge on one side and a negative charge on one side only on the surface, whereas inside their charges will cancel each other, and as a result of which there will be an induced electric field created, but not as strong as in the case of conductors. So there still remains an electric field which is less than the applied electric field. Our next topic of discussion is capacitor and capacitance. Capacitor and capacitance. You will again see capacitors when you study AC circuits, not now. Capacitors and capacitance. You can write down. A capacitor consists of two conductors, and I'm making the diagram by that time for you. A capacitor consists of two conductors. They can be actually in any shape. A capacitor consists of two conductors separated by an insulating medium. Separated by an insulating medium. So there is where the dielectric part will come. Initially, the capacitor that we will study is, we will use air as a dielectric or vacuum as a dielectric. A capacitor consists of two conductors separated by an insulating medium. One conductor, so these are known as your conductor. One conductor has plus Q charge and the other conductor has minus Q charge. So two conductors separated by a dielectric, equal and opposite charges. And how did you create these charges? We created these charges by connecting them to a battery. Connecting them to a battery. All right. So see how this happens. If you connect it to a battery, this is positive and this is negative. The battery is going to withdraw all the electrons from here. So this becomes positively charged and send all the electrons here. So you can write down, capacitor is connected to a battery. Capacitor is connected to a battery which removes electrons from one plate. So plate or conductor, plate becomes positive Q, and deposits electron on another. Here plate becomes minus Q. Okay. So what is a capacitor? A capacitor is an arrangement of two conductors, like two plates, which are separated by a dielectric. The capacitors plates are actually connected to a battery source, which will withdraw electrons from one side, making one plate positive charge, and deposit the electrons on the other plate, making it negatively charged. Is this okay so far? Okay. Now, the two conductors will such now develop potential V1 and V2, and there will be a potential difference V, which is equal to V1 minus V2. This is known as your potential difference. The potential difference is VD minus. And this PD, you can write, creates an electric field for the capacitor. For your sense, you can write this should be equal to E into D, right? If this distance is, say, D, voltage is always ED. We will come to it later when we see parallel plate capacitors, but you should know this. What is it? Due to the charge deposit, both the plates will be maintained at two different potentials, V1 and V2. This is a positive charge, this is a negative charge. So when you have positive and negative charges difference, you have two different potentials, and these potentials will create a potential difference PD. PD with a difference. D is the distance, okay? I have not yet explained it, but we'll come to it. And the electric field is set up due to this potential difference. And that electric field later will be governed by this law. V is equal to ED, where D is the distance between the two plates. But that we will come when we study what you know known as your parallel plate capacitor. Done? Now some findings. If Q doubles, V also doubles. These are lab finding. That means Q is directly proportional to V. If charge doubles means, children, what I'm saying, make it, this was 5 coulomb minus 5 coulomb, make it 10 coulomb, 10 coulomb. If the voltage was V, now the voltage will be 2V. Voltage means voltage difference. Bacha, voltage difference between the two. Always we are, this was some value 10. At 5, if it was 10, at 10 it will be 20. At 5, if it was, say, 5, then at 10 it will be 10. So when you have made it 10 on either side, the difference has also doubled, which was 5 has now become 10. Okay. So the ratio of Q upon V is always constant. This is from the proportionality study. And this constant ratio is known as C. C stands for capacitance. Stands for capacitance. Capacitance actually tells you how much charge, that is Q, can be stored per unit volt, that is V. How much charge can you store per unit volt? If you maintain a potential difference of V, how much charge am I able to store? Have you written this much? Did you understand this much? Now I'll write something which might be a little bit difficult to accept, but with an example you will understand. If Q doubles, V also doubles. Q is directly proportional to V. The ratio Q by V is constant, which is known as C, which is capacitance. How much charge can be stored per unit volt? Now let's see what we are writing now. So we write, if C is large, okay, look at this expression, C is equal to Q upon V. If C is large, more charge is stored, means you are increasing this and you believe that this has increased, then V should come down. So we say more charge is stored for same, more charge stored. That means, okay, 1 minute. Huh? If C is large, more charge is stored for, and voltage rise is smaller. The voltage will rise but will not rise that much. You are able to store more charge. Large capacitance means more charge stored without developing voltage. Voltage rise is smaller, means I can write without developing voltage. You are able to, a capacitor is basically a charge storage device. You are able to store more charge without developing much voltage. So it's like this. If C is equal to, we'll come to the unit. Huh? Let me just write. If C is equal to 1 farad, I'll come to this, just absorb it. And Q is equal to 1 coulomb, then V is equal to 1 volt. In the same segment, we say, if C is equal to 10 farad, Q is equal to 1 coulomb, then V has to be equal to 0.1 volt. Try to understand. If C is large, more charge is stored, voltage rise is smaller. In other way, you can say, if C is large, more charge can be stored, or for same charge, this rise is smaller. This is one option. Second option, we can say, if C is more, if C is large, this is option 1. More charge is stored. Option 2 is same charge. Same charge can be stored. Same charge can be stored with less voltage rise. That's what you did. See, when C was 1F, to store 1 coulomb, you need a voltage difference of how much? 1 volt. When C is 10F, you can store the same 1 coulomb with 0.1 volt. This you can understand very nicely with a water tank example. Water tank example. What is it? Capacitance. This is what you are studying. In the water tank, it is capacity. Charge. This is quantity of water. Voltage rise. This is rise in water level. Think yourself. If you have a bigger tank, then you store more water with less rise in water level. Got the idea? If you have a bigger capacitor, means whose capacitance is more, you can store the same charge with less rise. You can add more charge with less rise. It's like a 1 liter mineral water bottle and that can. That can store more water. Our friend Neha emptied 1 bottle of water in that from that can. How much is the dip? Just little. But if I would have kept a bottle out there and she would have emptied half bottle, the dip will be much more. So if your capacitance is bigger, you can store more charge with less potential difference. Kam mein aap zyada charge rakh sakte ho. Now did you get the idea? This is what is in terms of mathematics. Okay. The SI unit of capacitance is known as farad, given after Michael Faraday. Farad. 1 farad is the capacitance of a capacitor when it can store a charge of 1 coulomb with a potential difference of 1 volt. 1 volt. Right? You will later see 1 farad is a very, very big unit. We don't use. So the units used are microfarad, picofarad, nanofarad. This means 10 to the power minus 12, 10 to the power minus 9, 10 to the power minus 6. 1 farad is very big, and you will actually get the value also later. Okay. The capacitor was made out of what, beta? Plates and some dielectric and some difference between the dielectrics. Acha, a capacitor can be made with one plate also. The concept is the other plate is at infinity. You are unable to see. So sometimes they may ask you, can a capacitor theoretically have one plate? Yes. Where is the other plate? At infinity. What is the difference between them? Infinity. But usually the capacitor will have two plates with a finite distance across them, and it will be spread with a dielectric. So one more thing we will write. You might be thinking that the size of the plates matter and all. No, not at all. We write capacitance C depends on, it has nothing to do with those. It depends on charge, sorry, capacitance does not depend. This is very strange. Okay, one minute. Write it. Capacitance does not depend on Q or V. What is sir saying? He just wrote C is equal to Q upon V, and he's saying it does not depend on Q and V. This is theoretical, but when you manufacture the capacitor, it does not depend on C and V. Okay, depends on one, size of conductor. So it's a geometric property you will find. Size of conductor, distance between the conductors. In other words, if you want to write it in one word, this is known as separation. It depends upon the size, SSD we call it, size, separation, and the dielectric that you have used. Why dielectric? Because you just saw that if you have a dielectric, the net electric field reduces. V is equal to ED. So the V will get impacted when you put, and if the V comes down, if you put a, now you can analyze yourself. If I put a dielectric, the E comes down. If the E comes down, V is equal to ED. The V comes down. If the V comes down, the C jacks up. Therefore, if the capacitors that we get for all these are known as electrolytic capacitor, mica capacitors, tantalum capacitors, paper capacitors, you'll always have a dielectric. Our next topic is one type of capacitor which we study called parallel plate capacitors, and the derivation is done thinking that there is only air. Air is not considered as a dielectric. Air is almost like vacuum. There we will find that when you put air, the capacitance is less. But you take the same capacitor and with a syringe just push some dielectric between the two, the capacitance will go up. Why? Because the E falls down. If the E falls down, the V falls down. If the V falls down, the C goes up. Right? Different material, different. Larger plate, and if size of the conductor, if plates are large, larger plates, larger capacitance we will get. Obviously, where are you holding the charge? The charges are held on the plates. So if the plates are large, the capacitance is large. Right? I don't think we will have time, but you can write down. Just write down. We can't keep on adding charges forever. Now what our friend is trying to do? Our friend has taken two plates and then he or she has connected with strong battery, and she's on a spree of adding charges. You are going on adding charges. What will happen if you go on adding charges? The electric field will become very strong. It will ionize the air in between, and a huge spark will be seen. Right? And once the spark is seen, the charges are lost. What happens when you wear a sequin dress and you try to hold that curtain or something, that touch, something happens? You are also creating a capacitance only. You are charged, the curtain is charged, and the air in between. What is a spark? A spark happens when the air in between you ionizes. So we call that as, that thing is known as the breakdown of the dielectric. Every dielectric, when you see a capacitor, next time I'll bring one, you can see, it will be written 25 volts. Don't give it more than 25 volts, because if you give more than 25 volts, it's a charging voltage. If you're charging it more than 25 volts, then what will happen? The dielectric will get conducting. Its insulation will be broken. So that's what we are writing. We can't add charges forever. As Q increases, so see, if this Q, the plus Q goes up, the minus Q goes up, then the E between them also goes up drastically. As Q increases, V increases. As Q increases, V increases. Obviously, Q increase. Earlier we were at V1, V2. Now Q has increased. So we have become V1 dash and V2 dash. This has also increased. Therefore, our potential difference has increased. So we write E also increases. E also increases. And a strong E can ionize the air between the conductors. And the strong E can ionize the air between the conductors. Strong E can ionize the air between the conductors. Air becomes conducting. Air becomes conducting means, have you understood? The thunder happens. The same thing happens when lightning strikes. Air becomes conducting and charges leak away. Your job was to make a capacitor. You wanted to make a water tank. So you started so much of water storage that tank exploded. Charges leak away. This is called dielectric breakdown. You have broken down the dielectric. This is called dielectric breakdown. Last definition and we will close. Write the definition as dielectric strength. Dielectric strength. So what is your dielectric strength? My dielectric strength is the maximum E that I can withstand, which does not break down. So write down dielectric strength. The maximum electric field a dielectric can withstand. The maximum electric field a dielectric can withstand without breaking down. Without breaking down is known as dielectric strength. Is known as dielectric strength. Maximum electric field. For air, this is the value you can write down. Acha, why did I write voltmeter? You very well know V is equal to ED. So volt is equal to E into meters. So E is equal to volt by meters. Did you get it? E max for air is 3 into 10 to the power 6 volt per meter. So you can write a line. If field exceeds this value, air becomes conducting. Air becomes conducting. Sparks may appear. Sparks may appear and conductor, and capacitor loses charge. And capacitor loses charge. Capacitor loses charge. Okay. That's all. Let's have a quick revision, whatever we learned. Right. We started our story with dielectric. A dielectric is a substance which does not conduct electricity, does not have free electrons, okay? And there are charges which generally do not move freely like a conductor, but just shift. Due to such shifting, they can create some dipole moment. Dielectrics can be polar or non-polar. If you have a polar, in a neutral condition, you don't have any dipole moment. But if you are non-polar, you have dipole moment which are non-aligned. When you bring an external electric field, a polar can also have a net dipole moment. A non-polar will also have a net dipole moment. Such dipole moments do one thing, that is on the surface they create induced charges, but inside the positives and the negatives cancel. So each surface will have a positive polarization and another surface will have a negative. So polarization is with an external electric field. How did you make a dielectric, which was a non-conducting substance, get charges on its surface. Polarization is given by epsilon 0 xi e into E, where xi e is known as the willingness to polarize or electrical susceptibility. This much we had learned. After that, we started to understand what happens in a capacitor. So a capacitor is an arrangement in which you have two conductors separated by a finite distance. Usually it can be a single conductor also, where the other conductor is thought to be at infinity. That's a hypothetical concept. And the finite distance interspace can be filled up either by air or by a dielectric. When we study parallel plate capacitors later, we'll be having air filled in, but you can have a dielectric. So a capacitor is connected to a battery. As a result, the battery will withdraw electrons from one plate, make it positive charge, and will deposit the electrons on the other plate, make it negatively charged. As a result, both the plates will develop potential something like V1, V2, and a potential difference V will be created across the two plates. This potential difference will induce an electric field because V is equal to ED, right? We will create an electric field. Now, we have experiments show that charges double if the voltage is doubled. So Q is directly proportional to V. The ratio of Q upon V is known as capacitance, and it is defined with the SI unit of farad. 1 farad is 1 coulomb over 1 volt. 1 farad is the capacitance of a capacitor, in which 1 coulomb charge can be stored at a potential difference of 1 volt, right? Then further we saw, if you increase the capacitance, what happens? Same amount of charge can be stored with a less amount of voltage rise, analogous to a water tank, where if you increase the water tank size, the water level does not rise that much, but more water can be stored. Agreed? Then later on we will say that whenever you introduce a dielectric always has an induced electric field in it, which reduces the overall electric field. So if you induce a dielectric, the voltage will become ED. E is less, so voltage will fall down, and as a result, the capacitance will go up. But we cannot keep on adding charges in a capacitor, because if we keep on adding charge, the voltage will also increase, and as a result, the electric field will increase. This electric field can ionize this interspace between the two plates, that is, ionize the dielectric. As a result, the dielectric will undergo a dielectric breakdown, charges will leak, and the capacitance will lose its main property of storing charges. Understood? And that's why we define a term called dielectric strength. The maximum strength a dielectric can show, that is the maximum electric field it can withstand across it without actually breaking down. For air, it is this. Now understand, if you have seen DSLR cameras or any other cameras which use additional flash cameras, and you just turn on the flash, you will hear a sound, it will make a small noise, and the photographer will switch on the flash and wait. Otherwise, two batteries of Duracell, how are they giving this much of light? Two batteries torchlight you have seen, that should strike you. How is Amit getting so much? So he is basically charging a capacitor. Therefore, whenever a flash is switched on, immediately the photograph cannot be taken. The indicator will come green, means now you are ready to fire. So the battery is not powering that flash lamp. The capacitor is firing that flash lamp in one go. So in year of 1950s and 40s, if you see old movies, all those night photography used to be very costly. People who were very rich and used to photograph their evening shoots of night, the photographer will carry box of bulbs. Every shot, one bulb gone, because huge voltage is thrown across. Nowadays we have concepts like you have power banks. Now suppose you need some power banks for, say, the CMOS of the computer. You have a small cell. People are replacing those cells by supercapacitors. So when power failure happens, the capacitor starts draining. Capacitor acts as a small battery. Yeah, so it will drain. Again, when the power comes, the capacitor charges. All these fans and everything have got a capacitor. And that's why the microwave oven, if you have last used it and there have been 6 days which has passed, and the technician comes to open it, even if it is unplugged, the first thing he will do is just put a screwdriver and short the two ends of the capacitor. It can be lethal. Microwave capacitor is very, very high. It stores a lot of charge, and those charges are accelerated. So even if a microwave is turned off for 5 days and you open that plug, don't ever go and touch inside. The capacitor remains charged. His first job will take a screwdriver and discharge it. Even in air conditioners, there's always a capacitor. Discharge it. It can be lethal. This is like a storehouse of charge. Okay? So now next class we will